Greetings, folks. It's Professor Fiore, and welcome to part 4 of our Room Acoustics series. What I'm going to do in this particular video is walk you through a series of acoustic spaces and see how we're dealing with things like reverb time, acoustic isolation, sound isolation, things of this nature. So we're going to start with this interesting room, which is probably one of the more challenging acoustic spaces you can deal with, and that's an indoor pool. So this is a college's indoor pool. It's generally speaking all very hard reflective surfaces, right? I mean, you got the water, you've got basically concrete everywhere, concrete block, things of this nature. So how have the designers of this space tried to deal with this? Now, I should back up here just a bit and indicate that what we're seeing here is actually a refurb. This pool existed let's say in its original state, and then later on, some years later, it was modified. This entire building was modified. And as part of this process, they tried to do some acoustic treatment. So what, in fact, did they do? I mean, there's not a lot you can do as far as, let's say treating the walls. You can't put up, absorbing panels and things like this because, yeah, they'll absorb sound, but they'll also absorb water. You have to be really careful about that. So look up at the ceiling, right? These panels up here, these are not just, for visual effect. These are, in fact, absorbent panels. But they're basically on a second floor ceiling, right? Basically, here's your first floor. The second floor is right here. So this is fairly far up. We don't really have to worry so much about splashing water getting to this. So each one of these panels is angled, and there's a space behind it. Now what ends up happening is the sound comes up and enters the panel. So a portion of that's going to be absorbed. Remember the three things, right? Reflect, absorb, transmit through. So a portion of this is going to be absorbed. Some of it will transmit through, and then when it hits the concrete ceiling, it'll bounce back and sort of re-enter from the backside one of these panels again, which will reabsorb, right? Absorb again some more of this. So the idea here is to have enough surface area that we can really cut down on the RT60 of this room. And I've been in this room before we had the panels up here, and you could not have a conversation with, two people, one over here and one on the opposite side of the pool. It was ridiculous. You had to talk in a very slow, measured kind of way. If you just were shouting or something, it would just get lost in this haze of reverb, right? So certainly a challenge. All right, let's move along. Here we have the interior of a class/lab room. Originally, this was designed for art students. This had a lot of good light in it. It was subsequently used for, general sort of lecture space. The main problem with it is it does have a very high ceiling, so there's a good volume, and it's all hard surfaces, right? You've got all these hard surfaces out here. And again, the RT60 was really nasty. So, as a lab space for an art student, well, I guess that's not really a big problem. You're sitting there sketching, figure drawing, whatever the heck it is. But if you're trying to have a normal class lecture in there, it can be a challenge. So what they tried to do here was reduce the RT60 by putting in some absorbent panels. Now these are, I believe it's Sonex. That's a brand name, but it's a common thing that you can purchase. This sort of corrugated, expanded foam material. It's lightweight. I believe this is 2-inch Sonex. And the nice thing about this is it's really easy to adhere to the surface. You basically get some industrial glue, get up on a scaffold here. You squirt the glue down with a caulk gun, press the panel against the surface, in this case, this concrete ceiling. You wait about 30 seconds and you're good. You go on to the next one, right? So it's an easy install in that regard. This certainly did help the situation. It really wasn't enough. There wasn't enough of this on all of the surfaces to really bring this down to what I would call high intelligibility. You still had some RT60 issues, but it was an improvement, right? And it doesn't require any kind of structural change. In that regard, it's maybe a decent sort of middle ground that you could consider. I probably would have gone with some thicker Sonex. I probably would have gone with 4-inch Sonex, but be that as it may, that's an approach, right? We need to increase the absorption to cut down on that RT60. Okay, next. Here we have the field house. All right, so we've got obviously indoor courts and so forth. A field house is not known as a good acoustic space. Again, all hard surfaces, lots of reflection, not so much in the way of absorption. Well, what did the architects try to do here? It's not perhaps immediately apparent, but these panels here, and actually from the back of the photograph, the person who's taking the photograph, right, to their back, there's a lot more of this. So this helps to absorb, but you still have all these big glass areas. And this is all cinder block, right? But unlike normal cinder block, you can see that there's these weird little sort of black lines and dots and things. What the heck is that? Let's take a look. Here's a close-up of those cinder blocks. These are not standard cinder blocks. There are cuts in these. I remember when this was first installed, I went down there and I just had to investigate. So I walked up to one of these things, and you could literally stick your fingers in here, and there is a soft absorbent material here. And the idea is, again, instead of having just this big sort of acoustic mirror, this big hard surface that's just going to bounce everything back, we do have some, granted, not a ton, but we do have some absorptive capability here. So as field houses go, this is really not bad. It's not something you want to perform, delicate chamber music in, have a concert in there, but it's better than your average, let's say, field house, athletic facility. Moving on. Okay, now we're looking at the theater. So this is a space that really is designed, for maybe a chamber music concert or something along that line. What have they done here? They did a nice job. This is a good acoustic space. I've been to many, different gatherings and so forth in this space. So the first thing I'll point out, again, kind of like the pool, we have these large absorptive panels up here. And again, there's space behind them. So the sound goes through, bounces, returns. You get sort of it's kind of like a 2-for-1 sort of thing. The other thing, there are not a lot of large parallel surfaces, right? The ceiling slopes up. These walls are splayed out. And this helps with room modes, right? With the eigenmodes. This helps disperse things. This wall, and of course the opposite wall on the other side, you'll notice it kind of looks like it's corrugated. It really is. This is a series of panels, basically, that are indented alternately. You can tell by the shadows, okay? And again, this idea is to help diffuse the sound so you don't have these big flat areas where the sound hits and then bounces and you get really bad flutter echoes. So, this is a purpose-built space, right? It's designed with acoustics in mind, along with, of course, line of sight to the stage for the performers and so forth. But this is what you get when you take the time and you design properly for the acoustic environment. All right, now let's sort of shift gears here a little bit and consider something maybe on a smaller scale. I know some people are interested in maybe building a home media, kind of like a home theater room, something like that, or maybe a music space, a home recording space. So let's take a look at some construction on that, because I have been involved with such construction. So we talked about the idea of sound isolation. Remember, soundproofing is sort of a misnomer. You don't have perfect sound isolation, but you can really lower the amount of sound that goes through a barrier, through a wall. And that's a two-way street, right? You don't want to bother your neighbors, but you don't want the outside noise, trucks, buses, airplanes, to come into the acoustic space. So one of the things we do is we would make a high loss wall, which would be a multi-part wall. A double wall would be typical. So I'm going to show you the framing on that. Here we have a double, this is a double 2x6 wall. So here we have the outer sheath, and this is framed in for a window right here. But on the inside, right, here's the bottom piece, and we have the 2x6s running up, and right in here, there's about a 1 inch, say 2 or 3 centimeter gap to a second sill plate. And on that sill plate comes up, the other set of 2x6s. And you'll notice that these are offset, right? Except for the, obviously where you have to do the window framing, these things are all offset, right? Even the short one on the window frame, these are offset, and the major ones are all offset. So what's going to end up happening here is this inner cavity is going to be filled with fiberglass bats. And then this second wall will be filled, and you'll still leave a little gap between them. And then on the outside of this, we'll put on double layers of drywall with a viscous damping solution material sort of caulked in between those two. Just like the 2x6s here being staggered, the joints on the plasterboard, the drywall, will also be staggered. We don't want anything to line up. Okay? All right, moving along. So, by the way, think about this for a second. You're literally using twice the amount of material. Right? You're making 2 walls. You're going to use twice as much drywall. This can get a little expensive, but you're never going to get the kind of performance out of a single wall that you'll get out of something like this. Now, we also need to concern ourselves with the connection, the mechanical connection of that inner wall to the rest of the structure. You can't just take the inner wall. So here's the inner wall right here. Right? Here's another piece of it. So the outer wall, the exterior wall, is this right here. And this does have a sloped ceiling. Give it a little bit more volume. So here's your inner wall. Now, you can't just take this and nail it to the ceiling trusses, because now you have a problem with mechanically born sound transmission. So basically what happens is the sound hits this wall, it vibrates the wall, microscopically, you don't see it moving, but it's actually moving. And then that would get conducted up into the framing members up here, the trusses, and that would continue on out to, anything that's connected to. So we have to do some kind of isolation on that. And what these metal devices are is they are acoustic isolators. So this is just a little sort of L-shaped piece of metal, and then right here the black bits, those are large, quite large, because remember this is 2x6, rubber sort of like washers, compression items. And then a fastener is just driven down through here, but it's not directly connected. So you don't have this metal to metal or metal to wood kind of construction. You always have this rubber isolator, which is high loss, right? It's sort of a point source kind of a thing. And there's a lot of mechanical friction there, which dissipates the energy. So this way the sound hits the inner wall and it isn't mechanically coupled, at least not in any great way, up into these other framing members. So you have, sort of a wall within a wall almost. You can't just leave this freestanding. That would not be so good structurally. You have to do something to it. There isn't enough space here. In an extreme case, what you would do is you would make another set of framing members to hold these pieces together. But in this particular design, there wasn't enough space to do that. So this is the alternate way of achieving that goal. All right. Ideally, what you really want is a room inside of a room. and it doesn't touch anywhere, not even the floor. The floor would be, a poured concrete floor that's sort of resting on these big, massive damping springs. So it's like a floating room inside of a room. That's the ideal, but that gets pretty expensive, right? In any case, moving along, there are details and there are details. Something as simple as an electrical box. Got a plastic electrical box. This is like poking holes, in a plastic bag, and you're trying to hold water in it. This is a problem. There is not a lot of mass here. There's basically knockouts in the back, right, for the wires. So the sound can just enter through here, and it's short-circuiting this whole thing. All right. So this is the inner wall. You can see this pretty well. Here's the little gap. Here's the exterior wall, and obviously this thing has already been filled with fiberglass. So to help with this, what we do is we put basically it's fire clay that's wrapped around the entire box. All right, so that's very dense. It's not rigid. It's high loss as far as an acoustical wavefront would be concerned. So this thing is completely encased, right? So those little things, you maybe wouldn't think about that, but any kind of break in that wall is a potential for sound to get through, right? And the bigger they are, the worse it is. But even little tiny ones, you got something the size of a pencil, sound is just going to pour through there. It's terrible. So you have to be very, very careful. Even something like this, right? If you ignored this, you're just going to ruin the quality of this particular wall. Okay? Alrighty, now, what ends up, right? What do we end up with here after all of this work? Well, in this particular space, when it was finished, we put in a monitoring system and a white noise generator so that in the space, the SPL meter that we were using was reporting about 95 dB. I believe that was dBA. That was 8-weighted, if I remember correctly. So darn loud, 95 dBA. And then we went outside, probably, maybe 15 feet in front of the structure. And we've had measured previously the ambient noise, which was somewhere in the upper 30s, maybe 38 dBA. And with this sound source cranking out, outside, we measured just a smidgen above the ambient, maybe 40 dBA. 95 in, and 40-ish out. So we're looking at least 55 dB worth of loss through this. And this includes, by the way, a bunch of windows. And the trick on the windows, because the STC, if you recall, on a window, typical exterior window, might only be 35. So where do you get the extra? Well, heavy plexiglass inserts. You basically look for a thickness of plexiglass that'll give you the same mass per unit area that the drywall would have given you for that same space, right? So that's what was done. I calculated out that, put the plexiglass panels in, and there you go. As a test, we pulled the plexiglass panels out, and it was almost, when you stood outside, it was almost like the windows were open. You could tell the sound was coming from the window space, right? Because you got a wall that's 55, maybe 60 STC, and a window that's 35. So yeah, it seems like the sound is coming right out of the window. Effectively, it is in this regard by comparison. Put the plexiglass inserts in there, and whoop, that effect goes away. All right. So if you're looking to do something like this, build a space like this, there are some books out there. Don't just try to wing this. There are some things that are sort of counterintuitive. For example, a lot of people might think that if you had drywall in here, like right here, right above this, so you had like drywall here, drywall here, drywall here, and then the exterior wall, that would work better. The answer is no, it actually works worse. It's worse if you do that, because that's what we call a multi-leaf system. Basically, one element sort of couples to the next, which couples to the next, which couples to the next. It's kind of like hitting dominoes. If you keep the spacing big, it's much better off. So you're way, way better off taking the drywall you would have had on this inside space and doubling up on the outside space. Right? Much, much more effective. So if you are interested in that, I'll put in a couple of books that I've used that I can recommend for data in the comment and in the description. But if you do have any questions, how does this all work together? Certainly leave them in the comments section. I'll be happy to answer them. And until next time, this is Professor Fiore saying, have a good one.